and enjoy. Go ahead.
Okay, great, thanks. So this is a talk about a new project, which is part of a program that my collaborator Bowen calls the Entanglement Bootstrap. I think this is a good name for the program, though it may confuse some people at the Simons Foundation. And the goal of this program, at least so far, is to try to understand gapped liquid topological phases made of bosons, where, by the way, liquid means no fractons for now, to understand these things in terms of some simple axioms about the structure of entanglement in their ground state. And so far, this program has had some great success at understanding, basically from first principles, the theory of anyons in 2 dimensions. And so in this talk, we're gonna see a few things that it has to say about 3 dimensions, about topological order in 3 dimensions. And so this is work in progress with my student Jinlong Wang and with amazing UQM postdoc Bowen Shi. And I guess I should start by apologizing to Bowen for 2 things. First of all, for my poor pronunciation of his name just now, and secondly, for all of the imprecisions which I'm going to inflict on his beautiful, rigorous theory in an effort to try to convey the ideas in a simple way. So hopefully he'll forgive me. So just to put all the cards on the table, the kinds of questions that one might hope to answer. I'm not saying we're not going to answer all of these questions today, but the kind of long-term goal one might hope to move towards is understanding what are the possibilities for topological order in 3 dimensions, for liquid topological order in 3 space dimensions. In particular, what are all the universal labels that we would need to understand to classify all such things? And moreover, another goal, which is maybe a little more mathematical, is the following. When we put a system with topological order on some space, it's the universal data of that state produces topological invariance of the space. And so a very natural question, which I would certainly like to understand better than I do, is what is the relationship between those invariants and known invariants, or all possible invariants, that distinguish, say, 3 manifolds from each other, or which distinguish isotopy classes of knots from each other. And of course, there's a whole lot of work on related questions, and I'm going to do a really terrible job of citing it, and partly that's because a lot of that work is in the framework of category theory, which I need to understand better than I do. But in any case, I think there's a genuinely new perspective on these questions, which comes from this program. So let me explain what it is. So the idea of the entanglement bootstrap, the sort of well, I'll say what the axioms are in a second, but the most important ingredient, the central player of this program, is a notion called the information convex set. And the idea is to associate to each region of space, think of it as a subregion of a larger system, X, a convex set of density matrices, so which we're going to call sigma of X. And roughly, it's those density matrices on the Hilbert space of this region, which are indistinguishable from the ground state in the region. So that is, any measurement that you can do, local measurements within the region X, can't tell whether the system is the global ground state, or only, or maybe the excitations are just not in the region X. So that's the key reason that this is an interesting thing, because although we know it's the ground state in the region X, there can be excitations outside of X. And moreover, if those excitations are topological, they the say string operator in 2 dimensions, which creates those excitations, can be forced to go through the region X. So that is, the excitation can be linked with the region X, and therefore the set of density matrices, which look like the ground state in X, detects that excitation. Okay, so this this convex set of density matrices is a topological invariant in several important senses, in two important senses. So first of all, it's insensitive, and so this is, you know, all of this work that these folks have done has gone towards proving these statements. It's insensitive to small changes of the reference state, this ground state, if we stay within the phase. So that is, you know, really this information convex set comes with a label, which is a reference state, which I'm going to suppress everywhere. But here I won't. So it's independent of changes of that reference state within the phase. And secondly, it only depends on the topology of the region X. So we can also, not only can we deform the state in which we're computing this, we can also deform the shape of the region, preserving its topology. Okay. So a key result in the two-dimensional case is that
wait, can you go back a second?
Yes.
What is sigma?
Oh, sigma is a convex set. It's a set of density matrices. Yeah.
And you use different notation here. Is it the same or not? Sigma sub psi and sigma without the psi.
That's right. So everywhere else, everything is sigma sub psi, but everywhere else I'm suppressing the psi because I'm going to use the same reference state all the time. Yeah. Only for this equation I wanted to emphasize that it, you know, in principle it could have depended on which state we choose, but and the important thing I want to emphasize is that it only depends on the phase of matter that state represents, not on where we are within the phase of matter. Good. Was there another question?
Yeah, I wanted to ask about this equality. So psi and psi prime can be different on X. So obviously these sets can't be equal as like sets of density matrices, right?
Yeah, I guess I should put a squiggle here also. It's an isomorphism between them. Yeah.
So is that like a combinatorial isomorphism or something? What does that mean?
Okay, yeah. So I don't want to get too far into the weeds, but I guess the important things for me are that they're the same as convex sets. So they have the same extreme points. So a convex set is determined by its extreme points. Any other point in the middle is some convex combination of the extreme points. And so the real important data is the extreme points of the convex set, and those are the same.
But these sets just can't be equal set-wise. If they were, right, but for the same reason I just said psi and psi prime.
Yes, well, I mean that there's an isomorphism. Yes, indeed.
Maybe like a unitary transformation from one to the other.
Yeah.
Okay.
Yeah, good, thanks. You're right, I was a little bit liberal with the equal sign there. Thanks. Okay, good. So by the way, that was a good illustration of the kind of imprecision that I'm inflicting on the theory. So yeah, you know what you're in for. Okay, so a key result in the two-dimensional case is that the information convex set for the annulus is a simplex. So what I mean by that is that the extreme points are orthogonal to each other. There's a finite number of them, and we can associate those extreme points with anion types. So this picture is the key picture to keep in mind. So for each anion type, you can have a string operator with one end inside the annulus and one end outside, and you get a different extreme point of the information convex set of the annulus for each distinct type of anion, for each super selection sector. Okay, and from the information convex set, we can read off a lot of the data that we care about anions. In particular, we can read off its quantum dimension from the von Neumann entropy of the density matrix minus the von Neumann entropy of the reference state. And to see that this definition matches perhaps more familiar definitions, another thing we can do is think about the information convex set of the disk with two holes. And I claim that that produces fusion spaces for these anions. I'll explain in a little more detail exactly what I mean by that, but the important thing for now is that it produces a set of integers for each choice of three anion types associated with the three boundaries of this two-hole disk. And the definition I gave here of quantum dimension agrees with perhaps the more familiar definition as the positive solution of this equation. So this is a good definition of quantum dimension of anions. And okay, so I guess I should say what are these axioms from which all of these statements are derived? And they're really very simple, and they follow from an assumption of a strict area law. So that is the the assumption that the entanglement entropy of a region, well, okay, let's say a simply connected region, is strictly a term proportional to the length of the boundary minus a universal term. And a consequence of that statement is the following two axioms: that for any large enough regions of this topology that I'm describing here, these combinations of unknown entropies vanish. And the really important driving consequence of that is it means that various regions, sets of regions, are quantum Markov chains, meaning that the conditional mutual information between, for example, a region A, any region outside this thing, any disk outside this thing, and C, the region A relative to any region outside and B is 0. So the important thing about quantum Markov chains is that it means that the global density matrix on the union of those three regions can be reconstructed just from the marginals, just from the reduced density matrices on the subregions uniquely. And so that's the sort of driving technology here. Okay, and I guess I should say, so this statement is not too surprising. It's the statement that the correlations fall off rapidly in such a phase. And I guess I should emphasize this large enough assumption. Of course, in any lattice model, the area law is not an exact statement. It's rather an asymptotic statement about large enough regions, so that as you scale up the size of the region, any deviation from this behavior falls off. And so you should think that all the regions that I'm drawing are 100 gajillion lattice spacings big. Okay, that's the picture you should keep in mind, and that's why we can use these statements as equalities. Ideally, one would like a more robust version of the theory where these statements are only approximately true, and one could hope to approximately reconstruct various things. That's a more difficult thing, which nobody's done yet. But I guess we think that it should be possible. Okay, so I guess I should mention, not every conditional mutual information is 0 as a result of this assumption. For example, the topological entanglement entropy is the conditional mutual information associated with this combination of regions in the vacuum state, and that's visible within the theory. So it's this combination of quantum dimensions, as usual. Okay, so that was a lightning summary of the 2D case. I'll say a few more elementary things, but let me just say what happens in 3 dimensions. So it's actually extremely simple. The good axioms to use turn out to be exactly the same axioms with instead of an annulus, we replace this with a surface of revolution of the same picture. So this is a sphere shell. B is the shell of a sphere, and A is a ball. And similarly here, C is the top half of the sphere shell, and B is the bottom half. And with these axioms, the essential results that I just alluded to in 2 dimensions generalize to 3 dimensions. So in particular, the information convex set is still an invariant of both smooth changes of the region X or of the representative reference state of the ground state. And so a very natural question to ask is, what is the generalization of the annulus, which identifies all of the topological excitations? And actually, this turns out to be a long story. Let me so I'll start with 2 examples of spaces which label such topological excitations, and we'll talk. This will be enough to keep us busy for a little while. So one way to identify particle excitations is by thinking about a region X, which is a sphere shell, so the surface of revolution of an annulus. And so the picture you should have in mind is just like in 2 dimensions. Now we have one particle inside the shell and its antiparticle outside the shell. Another region which identifies a different kind of excitation is the solid torus. So the surface of revolution of these 2 disks, which looks like this. And the picture you should have in mind about the excitations is that we can have a loop which winds around one of the cycles of that torus, around the non-trivial cycle of the solid torus. And both of the information convex set for both of these regions can be proved to be a simplex again. And so the extreme points of those convex sets label particle types, but we'll see that there are more possibilities beyond this. So a key example, I guess, right? I should mention that a key example that we're gonna think about when we need to test some general statement is going to be 3D gauge theory with a finite group G, the solvable limit of which is the 3D quantum double model. And so let me just remind you what that is. So the Hilbert space is a tensor product over links and of some triangulation of the space that it lives on. When by triangulation, I mean like a CW complex, really. And on each link, we have a regular representation of the group G, meaning a Hilbert space spanned by states labeled by group elements. And the Hamiltonian is made up of star terms and plaquette terms, and the abelian case is just the toric code. And the important thing is that the role of the plaquette term is to demand that the flux around a loop, or around any contractible loop, equals 1. And the point of the star term is to make things gauge invariant, is to demand that, well, there are closed flux loops.
Hi, John.
Yeah?
May I ask a quick question?
Please.
So it's actually about the previous slide. So do you make any assumption for the scaling form of S in 3D? As in,
you mean what scaling form of S implies these axioms? Yeah, it's the same assumption.
oh, so I don't actually need the scaling form. I just need these axioms. That's
exactly. Yeah, the axioms are a consequence of the scaling form, and everything else follows from the axiom.
And then from now on, you just take these axioms and forget about that scaling form. That's right. Program. Yeah. Okay. Thank you. Sorry.
No. Thanks for asking.
Yeah, John, I also have a question on that slide.
Okay.
So for the loop excitation, it is possible there are some knot structure on the loop, right?
Good question. Yeah, yeah, that's right. So indeed, that's partly where we're going. So indeed, so this is the thing I've drawn here is the simplest possible loop, and we'll see that there are many other possibilities. Loops can be linked with each other. They can form knots. But I guess the thing I want to say here is that the knottedness of this loop alpha here is not detected by the information convex set of solid torus. Right, so it can do whatever it wants out here, and that won't change the state inside the solid torus. So if we want to be able to detect any differences in the topological excitation resulting from the thing being knotted with itself, which indeed there will be, we're going to need to think about a different region. And so we'll figure out what region that is later on. Yeah, good question.
Different topology.
Right, exactly. A region X of different topology.
I see.
Good. Okay, so in the particular case of the toric code, of the quantum double model, I can illustrate what these excitations are. And I guess I should emphasize the quantum double model in 3 dimensions is in many senses simpler than the quantum double model in 2 dimensions. In 2 dimensions, the particle excitations of the quantum double are labeled by 2 things. They're labeled by an irreducible representation of the group, and at the same time, a conjugacy class of the centralizer of an element of that. Sorry, I said it the wrong way. It's labeled by a conjugacy class of the group, and at the same time, an irreducible representation of the centralizer of a representative of that conjugacy class. In 3 dimensions, those 2 things are split into 2 groups of excitations. There are particle excitations, which are labeled by irreducible representations of the group, and loop excitations, which are labeled by conjugacy classes of the group. And the quantum dimensions are exactly what you think they should be, so that the total quantum dimension, the total dimension is equal to the order of the group. And alpha here is just the number of elements in the conjugacy class alpha. And you can ask, how do I know these things? So there are various ways people have studied the excitations of the quantum double model before, but within the information, this entanglement bootstrap program, there's a beautiful way to understand this, which, and the idea is, I guess it's kind of familiar to anyone who has thought about, say, computing the ground state degeneracy of the quantum double model on some manifold. The thing you should do is pick the minimal triangulation of the space on which you're putting the thing. So the idea of a minimal diagram for a region X is basically the same thing, except that there's a small difference in the way one treats the links and vertices on the boundary. Because we're imagining that the state that we get we get on this minimal diagram arises by tracing out some region outside. So anyway, the simplest way to figure this out is by studying a minimal possible triangulation of X and constructing the density matrices that satisfy the definition. Okay, so I'm going to use this notion of minimal diagram whenever I talk about the quantum problem model. I'm not going to say too much about it. Yes, please.
Can I ask a question?
Please.
So you said that the loop excitations are labeled by the conjugacy classes.
Yeah, these simplest loop excitations are.
Yeah, is that the only label? I mean, I guess I can imagine fusing charge on the loop and then get.
Great. So my answer to that is the same as my answer to Shreda's question. So you're right that there are also loop excitations that have charge fused to them, but they're not detected by the information convex set of the solid torus. So that's what I mean by, that's the adjective pure in this, did I say it here? Yes, pure loop excitations was meant to indicate that the solid torus only detects the loop quantum number. It doesn't detect any particles that are fused to it. And that's just because this region, it can't be linked with a particle, right? You see, it's just a donut.
Right.
So we'll have to think of a different region to detect. Well, okay, let me give away this one. So if instead you consider a torus shell, then inside the shell, there's a notion of inside and outside. There can be a particle, and that will detect more general loop excitations indeed, which can have particles stuck to them. Good.
Yeah, I'm sorry. Can I add a little bit on top of that? So yeah, one could indeed consider a particle right next to the loop excitation, but as you just explained, you don't want to think about those, that's fine. But there's a matter of way to formalize this theory so that I know the loop excitations are labeled by two group elements commuting with each other, and then we're thinking of the conjugacy class of such pair. So I guess you're saying the other group element is not detectable by here?
That's right. That's right. So I think the excitation that you're describing there is a pair of loops that are linked to each other. That's and right. Indeed, so you can think of one conjugacy class as associated with each of those loops. And the second one is indeed, it's not detected by this region, but it would be detected by the torus shell.
I see. Thank you.
Good.
I have a related question. Maybe it's the same question, but maybe you can clarify. So there are also some loop excitations that doesn't have any particle attached to it, but they're also not labeled by just one conjugacy class, right? Such as I think sometimes it's called the Cheshire charge.
Cheshire charge, I mean.
Yeah. So for example, in Z2 cross Z2 gauge theory, you have two Z2 gauge fields, A1 and A2, and you can have a surface operator of the form A1 cup A2. It's associated with the second cohomology of the group G.
At various times in my life, I've understood what Cheshire charge was. Right now is not one of those times. Can I ask you to explain this to me after the talk?
Yeah, sure. Yeah, okay.
Yeah, I think probably the answer is that there's some other region that detects that, and we can figure out what it is.
Typically, it has some triple linking number with some other loops.
Okay, all right, good. Yeah, so indeed. So if you allow the loop to link with something else, then more exciting things can happen. I think that's the simple explanation. Yeah, so there, maybe I should back up and make a general statement. Any three-manifold with boundary that you can think of is associated with some data of the theory. So for any topological order you pick, any three-manifold you pick has an information convex set and labels some data. So actually, so I've started by trying to focus on these two simple things, which have a very simple interpretation, and forget about a lot of the rest of the data. But actually, from this perspective, there's a rather overwhelming amount of data that one can consider, amount of universal data, and the question then becomes how to organize it into some minimal set of data, right? What is the minimal set of data? And I actually don't know the answer to that question yet. Okay, good. I'm going to go ahead. Thank you for the questions. Okay, so amongst that huge set of data that I was just describing, there's a very important distinction to be made into two classes of data. So some of it is classical, some of it is classical information that can be copied, and some of it is coherent quantum information. So for some regions, most of the regions that I've talked about so far, the information convex set is a simplex, meaning that the extreme points are orthogonal, and therefore these extreme points label independent excitations. Though that kind of label is classical information, everybody knows it. The dust in the room can read it off and remember it, and without destroying it. That's classical information. In contrast, other kinds of regions, other regions X, produce fusion spaces of those excitations. And really what I mean by that is that they can store some quantum information. The density matrices in the information convex set can store some quantum information. And an important structural theorem that these folks proved is that the information convex set of any region can be decomposed. So I'm abusing some notation here, into a bunch of sectors where each of those sectors is labeled by extreme points of the boundary of the region. So here, what I mean by the boundary is some thickening of the boundary. So for example, for the region omega here, what I mean by d omega is this sort of thickening of the boundary. And it's possible to prove that the information convex set of that thickening of the boundary is always a simplex, so that it's labeled by some orthogonal extreme points. So this index A runs over those extreme points of this simplex of boundary things. So in this case, the information convex set for this two-hole disk is labeled by extreme points of this annulus, extreme points of this annulus, and extreme points of this annulus. So that is 3 particle excitations. By this direct sum here, I just mean that the general element of this convex set is a convex combination of elements of these. I think that's probably not standard notation, but I needed to fit it on my slide. Okay. Moreover,
excuse me, John.
Yeah, please.
Just to clarify, so here, are you saying like there's always a finite set of simple types for those excitations, and everything else can be decomposing to these simple types?
Well, so here I'm talking about a particular region, right? A particular topology omega, right? And so I'm saying that, and the thing I'm trying to describe is the decomposition of the information convex set of that region. And I'm saying that it's labeled by sectors, which have these simple labels. The simple labels associated with components of the boundary. Did I answer your question?
Yeah, and it's always finite. The set is always finite.
Yeah, I think they proved it's always finite. Yeah. I don't know how to convince you of that right now, but I think it's true.
I'll believe you.
I think Meng is asking if there are finite number of simple objects in the like the modular two category.
Yeah, I think the answer is yes. I think that's one of the things that Bowen worried about a lot, but I didn't pay attention to it yet. I think there's a proof that it's always finite.
Maybe I can say a word about
okay,
it. So,
save me, Bowen, yeah.
The answer is yes, we proved it's finite, but we proved it based on the assumption that the local Hilbert space is finite dimensional. So yeah, in that case, the whole Hilbert space on omega is finite. Yeah, in this case, we show it's always finite, but in general, if you consider infinite dimensional thing, we don't know.
But if that's important, then suppose you have like a lot of lattice sites in a region, the dimension of the whole region still grows, right? Is there any issue about taking a limit?
Okay, I think our answer is based on the isomorphism theorem. As long as the region you consider, no matter how large it is, if it can be smoothly deformed from a finite site, then it's okay. It's
Okay, good. Thanks, Bowen. All right. So the second part of this theorem is that in each one of these sectors, the information convex set is this.
Another question. So
okay.
In ordinary TQFT, 2+1 dimensions, they are also more complicated observables, which are not just lines, but lines that touch each other and split.
Mm-hmm. Indeed.
And they also have a Hilbert space interpretation, like what you described, and they can construct, if you think of space as being a Riemann surface, you construct states on that surface. So correspondingly, in your system, there should be all sorts of other observables which are not of the kind you studied associated with the topology of every three-manifold.
Sorry, are you talking about 2 + 1 dimensions or 3 + 1?
No, now I'm going to, so in 2 + 1 dimensions, the observables are states on a Riemann surface. And the kind of observables you study become more and more complicated as you increase the Riemann surface. They increase the genus of the Riemann surface. And they correspond in terms of lines, like the analog of the Wilson line. The Wilson line can split into others and become more and more complicated.
Indeed.
The analogous thing in 3 + 1 dimensions is that as you make space an arbitrary three-manifold, there could be all sorts of, mixed space and arbitrary three-manifold. There would be all sorts of observables which label the different states that could be there. So it's not all clear to me that just working with lines and surfaces would be enough.
Oh, Nadi, absolutely. I only mentioned the lines and surfaces as a simple starting point, as examples of simple excitations. And as I tried to emphasize, if we consider other regions, they'll detect more complicated excitations. So right now I'm in the middle of trying to explain a dichotomy between classes of regions, some of which detect coherent information and some of which only detect classical information.
The reason I'm puzzled is that the space of observables that you will have is much, much more complicated than in 2 + 1. So in 2 + 1 dimensions,
well, this is related to the fact that 3-manifolds is more complicated than 2-dimensional manifolds.
That's all I'm saying.
Okay, I agree.
Yeah, much more complicated. And correspondingly, the kind of states, the kind of observables you would like to describe will be similarly more and more complicated. And it's not clear to me that you construct all of them just from lines and surfaces.
I totally agree, and in fact, it's clear to me that you cannot, and I will show you that in just a minute.
Okay, thank you.
Yes. Okay, good. So let me just finish stating this important theorem that within each sector, fixing the sector of the boundary of the region, within each sector labeled by A, there is the space of density matrices is the space of density matrices on a Hilbert space. A Hilbert space whose dimension is determined by the data of these boundary labels, and that dimension is some integer, some possibly 0, but it's some integer which is invariant, both of the region and of the topological order, which is associated with the number of fusion with a fusion Hilbert space, the number of a space of states into which these anion types can fuse. Okay, so for example, in the case of let me call it B sub 2, which is a ball minus 2 balls, so it's like the 2-hole annulus, but the surface of rotation of it, it's labeled by classical sectors are labeled by 3 particle types. That is 3 irreducible representations of G in the quantum double model. But within each of those sectors, there's a Hilbert space, which is the fusion space of those 3 particles, and its dimension in the quantum double cases are the structure constants of the fusion ring of irreducible representations of G, unsurprisingly. Okay, so as an illustration of the technique, maybe let me go through this quickly because I'm running very low on time. A simple thing to prove is that the total quantum dimension of the particles, the sum of their quantum dimension squared, is the same as the total quantum dimension of the pure flux loops. That you get the same total quantum dimension from these 2 things. And the key idea, and this is the reason I want to show this, is this notion of merging. So that is, if we have a state in the information convex set of AB and a state in the information convex set of BC, which agree on the shared region B, we can merge them into a unique state on ABC. That is, we can make a quantum Markov chain which produces a unique state which agrees on the overlaps. The reduced density matrices agree on the regions of overlap, and which is a global state on ABC. The resulting state is the maximum entropy state in the information convex set of that shared region, of the combined region, and the merging process preserves the entropy difference. So these are very powerful statements which allow us to prove, for example, that by merging two balls in such a way that you get a torus, a solid torus, you can relate the total quantum dimension of the pure flux excitations to the topological entanglement entropy. And by merging two balls in such a way that you get a sphere shell, you can relate the total quantum dimension of the particles to the same topological entanglement entropy. Okay, so this is a strategy that gets used a lot. So here's the plan for I don't think I'm going to get to all of it. I guess the main result that I want to talk about is a notion of braiding non-degeneracy. And then if we have time, I'll ask questions like, how well can the entanglement bootstrap distinguish different topological orders? I'll talk about the sectors that Nadi wanted me to talk about. And then I'll talk about the answer to the question that Shweta asked about excitations that are associated with knots. Okay, so the idea of braiding non-degeneracy is very simple. It's that every anion should braid with something. The idea is that it should be detectable from far away because otherwise it wouldn't be an anion, right? That's the simple idea. An illustration of this possibility in the 3D quantum double is that the number of particle types, that is the number of irreducible representations of G, you all know is the same as the number of conjugate classes of G, which is the number of these pure flux loop excitations. And so the braiding matrix between these excitations is at least square. And in fact, it's unitary and can be constructed purely within the information convex set of the solid torus. Indeed, it can also be constructed purely within the information convex set of the sphere shell. And it comes from taking the trace in a particular state, a particular extreme point of the solid torus, of the operator that moves the conjugate excitation around the torus. And this we can prove within the entanglement bootstrap that this matrix is unitary and that it implies a Verlinde formula, actually two Verlinde formula. One that relates the fusion of particles to the S matrix, and a second one that relates the fusion of loops to the S matrix. And I'm going to say a few words about the idea of the proof, but first let me illustrate it in the case of the quantum double model. So in the quantum double model, as I said, the particle excitations are labeled by an irrep, and the pure flux excitations are labeled by a conjugate class. So I want you all to think, what is a unitary matrix that's labeled by those two pieces of data? I'm sure many of you can guess what it is. But we can compute what it is using the minimal diagram. Okay, I'm going to give away the answer now. The answer is the character table. It's famously you can make a unitary matrix by normalizing it properly. And so the proof that whose idea I'm about to describe gives an independent proof of the orthogonality relation for the character table of any finite group. So in this case, the fusion data is the ring of irreducible representations, and the fusion data for loop is the algebraic classes. Okay, so the idea of the proof, maybe I shouldn't say too much about it, but it has two parts. The first part is to consider two sets of particle excitations and think about this observable in two different ways. One of them is to realize that it factorizes into two copies of this braiding matrix. And the other one is to first fuse these particles together into some particle C, a superposition of particles C, and then multiplied by the braiding matrix for C. And then the second fact is actually more interesting and crucial for showing that it's non-degenerate. Relies, okay, I won't explain the idea except to say that it involves the use of a region which merges together this solid torus and this sphere shell in such a way that they intersect only on part of what looks like their intersection. So this merged region ABCD is not actually a subregion of R3. It's something that you can't embed in ordinary space. And the existence of a global density matrix on this whole thing is the key idea in the proof that the S matrix is not degenerate. Okay, so maybe I'm going to skip this. Should I skip it? Okay, maybe I'll skip this. And let me talk about the graph sectors. So there's more than one way to fuse two loops together. One way you might think about doing it is just putting them on top of each other. But another way you might do it is have them share some segment and then fuse them together so that you get an excitation which is a graph, spatial graph. And this leads to a new family of sectors, which is detected by the information convex set of the genus 2 solid. So you can see that this graph is braided around this genus 2 solid, and the information convex set of the genus 2 solid is also a simplex. And so these are new sectors, and they're really different sectors. For example, in the case of the quantum double model, the number of extreme points of the genus G solid has this simple formula that Jinlong found. And so, for example, in the case of when the group is S3 and the genus is 2, the number of excitation types is 11. And I emphasize that it's 11 because the number of excitation types, the number of pure flux excitation types associated with the solid torus is just 3. There are 3 conjugacy classes of S3. And this number 11, notice, is bigger than just the number that you get by just taking 2 of these things, right, and just independently sticking them together. So there's new sectors that emerge from joining them together. Okay, and I claim that these excitations also enjoy a unitary S matrix. There's another a conjugate set of excitations with which they braid non-degenerately. And in the same way that the solid torus associated with loops is dual to the sphere shell associated with particles, the genus G solid, here I've drawn it for genus 2, is dual to a ball minus G balls. And the S matrix between these excitations and excitations that look like this, like what Nadi was describing, is unitary. Okay, maybe in the case of the quantum double model, this leads to some interesting.
Is it clear that this S satisfies SL2Z relations?
By SL2Z, you mean the modular group of the genus G?
Well, you called it X by analogy to the standard problem, I assume.
Well, I called it S because it's a generalization of the braiding matrix. Yeah.
Right. S has 2 definitions which tend out to give the same object. One is the braiding, and the other is the action of the modular group.
I see. Right. Okay. Good. So indeed, you might ask whether this thing is related to generators of the modular group for the genus G object, and I don't know the answer to that actually. It's interesting to ask how the mapping class group of the boundary of the surface acts on this thing. I don't know. Yeah, good question.
I think it's SL 3Z on the 3 torus.
Right. So the question is whether this is a generator whether part of this is the generator. Then yeah, I'm not sure. Indeed. Okay. So in the case of the quantum double model, this matrix is some interesting combination of representation matrices and invariant tensors, which we can independently prove is unitary from the, I guess you call it the Peter-Weil theorem. The simplest way to represent it is this tensor network. Okay, so in the last minute or so, let me say a little bit about knots. So when I talk about knots in the following, what I mean is a neighborhood of the knot, so some tubular neighborhood, some region of 3 space. And okay, so humans have studied knots for more than a century. And an important question is whether they can be formed into each other without crossing. And in some sense, a complete answer to that question is the fundamental group of the complement of the knot. So some folks proved that this is a complete invariant. That is, that this is the same if and only if the 2 knots are related by isotopy. That's not, the analogous statement is not true for links. But these things are horrible infinite groups. And it's actually, it's provably hard to tell when 2 of these things are the same. And so the way that mathematicians usually make finitary data out of this knot group is by considering representations of it in a finite group. And this, one familiar non-invariant associated with representations of the knot group is coloring, 3 colorings of the knot. So 3 colorings of a knot are related to representations of the group of the knot group in S3, or more accurately, the dihedral group, the symmetries of a triangle. And the 3 colors are associated with the labels of the 3 possible inversions in the dihedral group. So, okay. And I guess maybe I should mention, then there's a nice presentation of the knot group, which associates generators of the group to arcs. That is arc, this is an arc of the diagram, and associates relations of the group with crossings. So this is a crossing. Okay. And so previous work has made connections between gauge theory and classification of knots. And I guess the work that I'm familiar with regards this representation of the knot group as a flat connection on the complement of the knot, thought of as a critical point of the Trent-Simons functional. And then these guys do Morse theory on the space of such flat connections. And they've proved some beautiful things about it. One thing I'm not sure if they're done proving that, but they've given an independent proof of the 4-color theorem in this way. So here we're going to think about gauge theory and knots in a slightly different way. We're going to think about discrete gauge theory, say living on, well, okay. So we can think about discrete gauge theory living on the complement of a knot. And I'm going to say this slide in just 2 sentences. So it's maybe a familiar fact that the ground states of the abelian quantum double model, that is the toric code, compute the first homology. So ordinary one-form toric code produces the first homology of the space. And the quantum double gives more refined data. The ground states of the quantum double model are homomorphisms of the fundamental group into the gauge group G, modulo conjugation. The idea is just demanding that the star terms give 1 produces closed loops, and demanding the plaquette terms gives 1 produces the homotopy equivalence. So the quantum double model gives more information than the abelian toric code. And so my point in mentioning this is that ground states of the quantum double, if you put it on the complement of a knot with appropriate gap boundary conditions, are representations of the knot group. So that's exactly these knot invariants that we were just talking about. So in particular, if you consider ground states of the quantum double for all G, you could detect all of the knottedness. But this means that the information convex set associated to the complement of a knot is a generalization of that. It's more information in the sense that now we're not demanding that it's a ground state everywhere. We're allowing for excitations outside of that region. And so we can hope that it has more information. Okay, so one way you might have thought to associate an information convex set with a knot would be just to take the information convex set of the knot itself. This detects excitations which wind around the knot, but this is boring. So in fact, this set is the same. Here I mean, of course, with squiggles. I mean, isomorphism, not equality. It's the same as for the unknot. But the information convex set of the knot complement does know about the isotopy type of the knot, and it encodes, the way you should think about it is as a fusion space for ways of creating from the vacuum a knotted excitation, like Schrader was asking about. So that is a loop excitation in the shape of a knot, perhaps with some particle excitations attached to it somehow. So the membrane operator that creates such an excitation is a Seifert surface for the knot. So something like this for the trefoil. And the information convex set is a knot invariant. So I find this idea very appealing because mathematicians really like this notion of categorification of invariants, where you take some invariant, which is an integer, and then find a Hilbert space whose dimension is that integer. So here it's like that, except instead of a vector space, we're associating a set of density matrices with it. So it's like a generalization of categorification. So far, we've been computing these information convex sets for the quantum double model for various knots and links in spatial graphs using this minimal diagram technique that I mentioned. This is an illustration of what that looks like. And the demand that rho is a ground state in the region means that we have to impose these plaquette conditions, which we can see very directly imply these Wertinger relations for the knot group. So it's like, how to say, I want to say that it's like a representation of the knot group, but of course it's not a representation because we're constructing a family of density matrices, not an action on some Hilbert space. And so one surprising thing that I can tell you that we found is that, for example, for the case where the group is S3, a single trefoil knot excitation, a single excitation with this shape, can store quantum information. So in the same way that when you take, in 2 dimensions, you want to do some quantum computation, you take some anyons And then you take some anions in particular, which have non-abelian fusion, right? Two anions, which when you fuse them together, have multiple fusion channels. So when you put them together, there's some Hilbert space associated with how you fuse them. And you can store some quantum information and manipulate them. Here, just a single trefoil knot has such a non-trivial fusion space just by itself. It can store quantum information. So I think that's a pretty cool thing, which I hadn't appreciated before. Okay, so let me make some concluding remarks since I'm out of time. So as I've tried to emphasize, any three-manifold has a role to play in this story. So far, I've given thus far a very incomplete list of possible excitations, and of what regions detect what excitations and what regions detect fusion of excitations. A natural question to ask is whether there's a sort of minimal set. In 2 dimensions, actually, these folks proved that we can stop at the 2-hole annulus. So that is, this fusion data associated with, say, the 3-hole annulus is determined by the fusion, at least the multiplicities of the 2-hole annulus. I'm not sure, I don't know yet what a notion of minimal set in 3 dimensions would be yet. But one thing that I find very interesting is the following possibility. It's possible that that there's a pairing between 3 manifolds. So that for each 3-manifold, there's a notion of a dual 3-manifold, where the information convex set of the dual 3-manifold detects the excitations in the original one. So for example, we've seen that there's a pairing between the solid torus and the sphere shell, and more generally between the genus N solid and the ball minus N balls. Another example, which I didn't mention, is the ball minus the solid torus is self-dual. It detects its own excitations. And there's some regions for which we haven't figured out what the right notion of the dual space is, or indeed even exactly what the right definition of the dual space is. But it seems like this is a mathematical fact that I haven't heard about before, which I'm very interested to understand more. Okay, so that's the end, and I guess I have to end by thanking my vice chair for assigning me to teach group theory this quarter. That was extremely helpful for me being able to keep up with Bowen on this project. So yeah, thanks for listening.
Yeah, yes, thanks, John, for the very exciting talk. We already have some questions during the talk, so I will stop the recording.